Hey, welcome back to Calculus. And in this third and final video, we're going to take a look at the last topic in section 2.3. It's a very long section, very important section. I hope you're working on all the homework problems and coming to office hours to ask me about things, and we can just talk about them. But the two more things I want to show you in this section is that sometimes it's best to handle limits one-sided. I want to give you some examples of functions where it's appropriate to kind of look at limits one side at a time. And then I want to show you a result that people usually call the squeeze theorem or the pinching theorem that can give you a technique to handle limits in a certain special case. All right. So let's start off. I've taken some material from the text just to make it a little cleaner here. But like I just said, the author is agreeing with me, or I'm agreeing with him, that some limits are best found by handling the left and right hand side separately. There's various reasons that that might be true, but sometimes if you're stuck on a limit, you can just remind yourself, well, maybe if I just look at it from the left, maybe I look at it from the right. And you remember from our work in section 2.2 that a two-sided limit exists if and only if the one-sided limits both exist and have the same value. All right, so you can answer the question kind of one side at a time. Let's look at this first example. Why would I handle it one side at a time? Well, because it's got an absolute value in it. I'm taking the limit as x goes to 0, and well, the absolute value of x depends on whether x is positive or negative. Maybe you guys remember, let me write it over here, that the absolute value of x is just x if x is greater than or equal to 0, but it's the opposite of x if x is less than 0. Yeah, maybe you're surprised that I'm writing the absolute value with this minus over here, but the opposite of x is not necessarily a negative number. In fact, it's not a negative number if x is a negative number. So this is how the absolute value function works. So if we took a look, say, at the limit as x approaches 0, let's start from the right, of the absolute value of x over x. Well, if you're approaching 0 from the right, then you're positive. So those absolute value signs don't do anything. So this is the same as the limit as x goes to 0 from the right of just x over x. And if x isn't 0, x over x is equal to 1. So that's the limit as x goes to 0 of the constant function 1. So the right-hand limit is equal to 1. Okay? Let's take a look at the left-hand side. That went pretty smoothly. Let's see how it goes on the left-hand side. So if we take the limit as x goes to 0 from the left of the absolute value of x over x, well, on the left, if x is coming to 0 from the left, it's always a negative number. So when you erase those absolute value signs, when you're trying to simplify this expression, you have to replace the numerator with the opposite of x. And again, if x isn't 0, the opposite of x divided by x is always negative 1. So the limit as x goes to 0 from the left of negative 1 is negative 1. So the left-hand limit is negative 1, the right-hand limit is positive 1, so the two-sided limit doesn't exist. By our fact that we can still see at the top of the screen there, we computed this left-hand side, we got negative 1, we computed the right-hand side, we got 1. Those two things weren't equal to each other, so the two-sided limit doesn't exist. Absolute value, dead giveaway for looking at things one side at a time. If there's an absolute value in the expression, you look at the limits one side at a time because the absolute value behaves differently on different sides of the origin. Let's look at a second example. It's a perfect example for a one-sided limit investigation too, because this function is so-called piecewise. It's given piecewise. What do I mean by that? I mean the function has different formulas depending on the input. If the input is bigger than 4, I calculate the output with this square root. If the input is less than 4, I calculate the output with this linear function. Notice that this function isn't even defined at 4. If x equals 4, 4 is neither bigger than 4 nor less than 4. So f of 4 isn't even defined. But you don't have to have it defined at 4 to talk about the limit. Yeah, but I'm going to look at this thing one side at a time because which side of 4 I'm on is governing what formula I'm using. So if we take a look at, say, the limit as x goes to 4 from the right, I guess I'm in the mood to start from the right today, of f of x. Well, that's the limit as x goes to 4 from the right, and I'm going to choose the formula x minus 4. and pause the video or write me an email or come to my office hours. Even better, if it's not clear to you, ask me why I chose x minus 4 square root. I chose it because I'm taking the limit from the right. So x is bigger than 4, and that's the governing formula. All right. So now by the direct substitution principle, if you let x approach 4 of this square root, well, you're going to get the square root of 4 minus 4. You're going to get 0. So the right-hand limit is 0. What about the limit on the left? Maybe you can pause and work it out before I do. The limit as x goes to 4 from the left, well, this time I'm going to use the linear function. Same reason. If I'm coming at 4 from the left, my values are less than 4. The formula that governs such things is 8 minus 2x. By the direct substitution principle, this is 8 minus 2 times 4. That's 8 minus 8. That's also 0. Okay, so here in this case, the left and right hand limits were equal to both equal to 0. So we can say, okay, the two-sided limit is 0 by that principle. Left and right hand limits are the same. Two-sided limit equals that. Piecewise functions always want to be considered one side at a time. I think I got a picture of this function down here for us. I didn't know how much room I needed, so I was cautious. This is a picture of that function. In my messy handwriting down here, you can see that I wrote the formula again. Maybe I can slide it up there and use some more room. And does this picture make sense to you? Let's kind of color code a little bit here. Let me pick a new pen. When x is bigger than 4, it's given by the square root function. Here are the x values that are bigger than 4 on that axis, and the corresponding graph is this square root. And you can see as x approaches 4 from the right, so you just watch the tip of the laser pointer, it's getting closer and closer to 4. What are the corresponding y values doing? Again, and watch the tip of the laser pointer. And well, as the x coordinate gets closer to 4, the y coordinates are getting closer to 0. That was the limit from the right that we computed up there. Yeah, if we do the same thing, looking at limits, the values of x that are less than 4 is to the left of it. So if we're coming in on that side, the corresponding part of the graph is this guy. So again, as x approaches 4 from the left, look at the tip of the laser pointer. What's happening to the corresponding y coordinates? Well, they're also approaching 0. Okay. Why does that function have a little circle there at 4? Well, f of 4 isn't defined. It's not defined. There's no value of the output at 4, but as x approaches 4 from either side, the output values approach 0. All right. So one last result from this section. It's called the Squeeze Theorem. It's got kind of a fun name. And so let's try to walk through what the author is telling us here together. So what are we saying here? You have 3 functions, f, g, and h, and they satisfy these inequalities. That can be a little bit intimidating when you look at that. F of x is less than or equal to g of x, which is less than or equal to h of x. But all it means is that if you pick any given x value, then on those 3 functions, the smallest y coordinate for that x value is on f. F is the smallest. G is always in between. H is always the biggest. So I've kind of muddied that picture over there. In fact, I hope this isn't annoying, but I'm going to kind of zoom in on it a little bit. Those inequalities that you're looking over there on the right-hand side, they just mean, I don't like my little marks, I'm going to get rid of them. They mean that the graph of G lives between the graph of H and the graph of F. Yeah, F is on the bottom. It's always below the graph of G. H is always above it, at least in some neighborhood of A. Okay, so that's that part of the hypothesis. The second part of the hypothesis of this theorem is that F and H have the same limit. They have the same limit at A. And the conclusion is that G has that limit as well. So why is it called the squeeze theorem? Well, because G is stuck between H and f. And h and f have the same limit. They're both going to L. So G is squeezed in to have that same limit as well. Yeah. If you and I or sorry, if you are stuck between me and some other person, and me and that other person are going to the same place, you have to stay between us. You're going to that same place. It's not a proof of the squeeze theorem, but it's a fairly intuitive result. The picture is very convincing. We would need a rigorous definition of limit in order to give any kind of rigorous mathematical proofs. So let's end this lecture by just illustrating how one can use the squeeze theorem to compute a limit. So it's kind of a trickier theorem to use than some of these other limit laws that we've been looking at, because you're typically only given the G. You have to invent the F and the H, okay? So you have to, something has to come from you. So I want to look at this limit, this function, x squared times the sine of 1 over x. And I'm looking at it as x approaches 0. Notice 0 is not a domain of this function. You might remember that we looked at the function sine of 1 over x in the section 2.3, and that thing had no limit at 0. But here we're multiplying the sine of 1 over x by something that's also getting small. Okay, so here's how we can kind of use the squeeze theorem. You remember from trigonometry that the sine of any real number never exceeds 1, but it's always at least minus 1. So that's from a property of the sine function. So if x is any real number except for 0, its square is positive. When you multiply inequalities by a positive number, you don't change the inequalities. So our function that we're interested in, x squared times the sine of 1 over x, is bounded between minus x squared and x squared. So you don't have to name them, and I'm not going to write the names here to keep it simple, but this is my f of x minus x squared. G of x is the thing I want to take the limit of, and that's my h of x. And the inequalities are satisfied. And moreover, if we take the limit as x approaches 0 of minus x squared, or we take the limit as x approaches 0 of x squared, we get 0 in both cases. Yeah. So our function g is bounded between two functions that have the same limit at 0. So the squeeze theorem says that g has that limit. It's squeezed in between two functions, both of which are going to 0. So we'll end this with a little graph. I've got it down here. Again, I didn't know how much room I needed, so I was a little cautious. But here is a graph of the function g of x. It's drawn in pink there, x squared times sine of 1 over x. It's a very interesting looking function. So because of this x squared term, the amplitude is getting smaller and smaller in that wave as we approach 0. But the sine of 1 over x, the 1 over x is approaching infinity as x goes to 0. So the sine function is going through its period more and more often. So if we looked at this thing as x approaches 0 from the right, it's oscillating, but it's oscillating less and less. That's because of the x squared, but it's oscillating faster and faster. That's because of the sine of 1 over x. But this is a beautiful picture illustrating how it's squeezed. Our inequalities that we wrote above, I think I'm going to write them down here again. Minus x squared is less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. You can see those inequalities in this picture, that pink curve that's oscillating is bounded between the blue parabola, that's the minus x squared, and the green parabola, that's the x squared. Those parabolas have the same limit. They're both going to 0 as x goes to 0. So the squeeze theorem says that's what happens to x squared times sine of 1 over x. Okay, so thanks for listening.